Recording is rolling. It is Thursday, February 12th. Foxboat Buoyancy Lab A. So you guys have this lab page, you guys have a square of aluminum. They give you guys some reminders of some concepts from lab 2 days. So guys, what Greek letter is this right here?
It's density.
Yeah, Greek letter rho, which stands for density, mass per unit volume. Guys, what's the density of water? Yeah, 1 gram per cubic centimeter. That's true. And how many kilograms per cubic meter is that? Yeah. So you got 2 different numbers for density of water, depending on the units. 1 gram per cubic centimeter, that could be helpful today. 1,000 kilograms per cubic meter, maybe not helpful. Okay, gauge pressure. The deeper you go into, oh yeah, guys. I'll bring you some stuff here. The deeper you go in the water, the more the pressure. So rho GH, density of the water, times gravity field times the depth, right? This pressure. Okay. Now, because objects are three-dimensional, guys, is there more pressure on the bottom of the object or on the top of the object? Bottom of the object. That tells you something about the direction of the force that results, which is going to be upward, and the magnitude of the buoyant force ends up being rho VG. Okay, so this V is the displaced volume, so here's some other kind of expressions right there. Okay, and actually, wait, I just switched, guys. That's Archimedes' principle. Says that the magnitude of the buoyant force is equal to the weight of the displaced fluid. Okay, so you guys remember all that? Okay, so now we're back to physics. Now we're back to this lab. So take a look here. So goal, guys, everybody look up here. You need to think deeply about this. This was a real challenge from our last lab. Goal: design a box boat with this square of aluminum to maximize the weight that the boat can carry. And we're all going to go with the same design principle here, which is that we're just holding up the 4 sides around the perimeter to create the. Okay. Now it's up to you, or you can treat this x, how much you fold up the side, as a variable. You guys see that? Okay. Because the more you fold up the side of the boat, what happens to the size of the square base? It gets smaller and smaller. Right? Now, if you don't fold up the sides at all, you just have a flat square. Can this hold any weight in the water? Probably not. I mean, maybe the surface tension will hold it up, right? But if you start attacking lab weights, it's going to just immediately sink, isn't it? Right? So you start to pull up the side, but you guys just told me that there's a trade-off. Right? The more you pull up the side, the square base is going to shrink. Now, to make a tall, skinny boat, is that going to hold very much weight? Right. So if you're trying to optimize the dimensions of the boat to maximize the weight that it can hold, I bet there's some optimal value you can fold to the side. You guys get that? Right. Right. So that's the premise that we're going for here. I just help you guys out. Can you guys draw a free body diagram on the boat and correctly label the force vectors, draw them proportional to scale? Buoyant force is what times what. Weight is what times what. What's the density of water? Oh, hey, look at that. We just went over the answer here. I got 2 perspectives on the density of water. Grams per cubic centimeter, kilograms per cubic meter. Okay, what's the gravity field on Earth? Yeah, guys, what is Earth gravity? Yeah, you can do 9.8 meters per second squared. Guys, how many centimeters per second squared is that? Yeah, okay, 980. Right. So, guys, throughout today, when you're punching numbers in the calculator, guys, look up here. You got to think deeply about this. Make sure that all your units are consistent. So, if you want to work with straight base SI units like kilograms and meters, then that'll never steer you wrong, although the numbers might be kind of small. Okay. And if you're working in centimeters and grams, then, well, just be aware that your units have to match. Right? Right. Especially when you get to this box down here. See where it says maximum weight is so many newtons? Okay. Guys, what does 1 Newton break down into in terms of base SI units? Take Newton section. Kilogram meter per second squared. Guys, look up here. Is this like Newton's second law of motion? F equals ma. So you can always reconstruct that. Okay. But guys, what if instead you were working not with kilograms but grams, and you're working with not meters but centimeters, and you came up with some unit for force, but it was in these weird units, grams, centimeters per second squared. Could you figure out how many newtons that was equal to? Could you do that? Here, I'll help you guys out a lot right here. This can really help. Guys, how many grams in a kilogram? 1,000 grams in a kilogram. How many centimeters in a meter? 100 centimeters in 1 meter. Okay, so if you take grams centimeter per second squared, some number associated with that. Maybe it's like 1.1 or whatever. Okay. and you divide by, what does this multiply out to right here? 100,000. Okay, so we're calculating your forces. Okay, make sure in newtons. That might possibly be a helpful conversion. All right, I have some. While I'm talking about railroad track tables, okay, there's also another one back that's just for volume, so that can help you out convert cubic centimeters to cubic meters. All right, got serious questions here. Right, y in terms of x. So as you fold up the side of the square, but fold around the perimeter, some amount x. Okay. Can you guys find? Do you guys see? I have the square base. Each side of the square base is labeled y. Do you guys see that? Can you guys come up for an expression of y in terms of how much you fold up side of x? Can you guys do that? Okay. And then right beneath that, can you guys come up with an expression for the volume in the boat in terms of x and y? And you can use this picture. You can play out this picture. I've set that up for you. What is the volume in terms of x and y? Now, guys, take those. Guys, think deeply about this. Guys, look up here. Think. Okay. You have y in terms of x. You have volume in terms of both x and y. But you also know x and y are not independent of each other. That's from this equation up here. That leads to the next question. Can you come up with an expression for the volume of the boat strictly in terms of x, the amount that you fold the side? Can you guys do that? See if you can do that. Okay. And now, guys, show of hands. How many of you guys are in calculus? I think about half of you guys are in calculus, right? Okay. If you do, there's a prime calculus opportunity right here. Because remember, you're trying to maximize the weight that the boat can carry, which has something to do with its volume. This expression is going to be volume strictly in terms of x. And if you're in calculus, this is a good opportunity to find an optimal, to apply calculus to determine an optimal value of x to maximize the carrying capacity of the boat. Okay. And if you're not in calculus, which is about half you guys do, that's okay. You can just do trial and error. And that's what this table can be really helpful for too. So different values of x. Like x could be 0.5 centimeters, 1 centimeter, 1.5, 2, 2.5, 3. I might actually recommend using those particular values. All right, so what would the corresponding y value be? Volume, maximum volume force. Okay. And then, of course, you can sit here and do calculations on paper, but you guys also have these little lab weights. So you can stack the lab weights in your boat and you can gather empirical observations. Okay. So what's the maximum weight that your boat could carry? Right, and see if you guys can figure that out. Right. On the back, a couple of graphs. And I have scaled graphs for you already. That might be a huge hint as to the order of magnitude, the answer that you're looking for. Okay. First graph is possible boat dimensions. What is y in terms of x? Okay, so x you fold up the side. Y is the value of the remaining side of the square base. Okay. And then over here, what's the maximum carrying capacity of the boat? What's the maximum weight it can carry in newtons? As a function of x, how much you fold up the side. Okay. Hey guys, look up here. Think about this. Okay. Now, what do you think the basic shape is going to look like? Like, guys, if you don't fold up the side at all, how much weight can your boat carry? Yeah, basically zero, right? Ignoring the surface tension. Okay. Now, if you fold up the side, you're going to be increasing the volume of your boat up to a certain point, but then there's a trade-off. Maybe if you fold too much, it's not going to be helpful anymore. Is that true? Okay. So, what do you think that means for the overall shape of this graph? Is it going to increase for a while and then probably turn around and decrease? Right? Okay. Do you guys kind of see that would make sense? Okay. Now, I will tell you guys this also. Guys, this will not be a parabola. So, it will be some other shape. Okay. In fact, what this shape is the graph of whatever this equation is right here, being in terms of x. Okay. All right. So, yeah. All right. See if you guys can figure out how to optimally design the boat to maximize the carrying capacity. Oh, guys, if you finish everything in class today, which earlier my class about half one did, you can turn this page into the grade tray and get lab points. I want, of course, all these algebraic expressions, some table values, have to figure out what's the maximum weight the boat can hold, and also make the two graphs. So if you have all of that, you turn it at the end of class. There should be enough time. If you don't quite finish all that, like you don't get to the graphs, so you can do that tonight and turn it in tomorrow.